And there we go. Okay, so so here's a new topic for today. So we finished 1, 2, and 3 last time, starting off now with 1.4. So the cross product, I hope y'all have seen the cross product in Math 218 at least a little bit. There's a lot of really interesting things to say about cross products and determinants and related ideas. I'll remind you that there's tough choices that have to be made in this course, and so the tough choice I've made for section 1.4 is since it's a tool to be used in calculus, but it's not really a primary focus of a calculus course. What I'm going to do is I'm going to go through all of the facts about cross products and determinants and such, but I'm not going to focus on proofs. There are a lot of proofs and arguments and reasons and connections and stuff made in the notes here, and I hope you'll take a look at them. They're really interesting. I think it's really beautiful stuff. But I'm not going to focus on it in the course. So the proofs that are in this cross product section, you're not responsible for. But again, it is very cool. Okay, so the first thing I want to talk about is, and this is an idea that's very closely connected to cross product. Something important to understand is what I like to call the geometric order of a list of vectors. And so we're going to start off in 2 dimensions. We're going to consider if you have 2 vectors in 2 dimensions, but specifically, it's not just that you have 2 vectors. You have an ordered list of 2 vectors. So this is not the set including the vectors A and B. This is the ordered list. A is first, B is second. Not because of alphabetical order, because I chose to write them that way, and I'm interested in having written them in that order. Okay, so let me emphasize, in this case, the way I have it drawn, A is first, and B is second. Okay, so with that order, let's talk about what the vectors look like. Of course, I still haven't, as of writing this list, I haven't showed you geometrically where the vectors are. Suppose that A were this vector. Again, that's the one that's first. And suppose that B were this vector. And again, remember that means that that's the one that's second. How would we describe this list in terms of the directions that those vectors point? And well, if you think about it, first, second, right? First, second, kind of suggests that we're going in a counterclockwise order. So this ordered list, A comma B, where this is A and that's B, that's what I'm going to call a counterclockwise order. Okay. Now, on the other hand, let's suppose that the vectors were different. Let's suppose that, now again, A is the first one. Let's suppose this was A. That's the first one. And let's suppose, now again, keep in mind, B is the second one. Let's suppose, what's going on here? There's my B, that's the second one. Given these vectors in that order, first, second, right? This one we would reasonably call clockwise. So these are the 2 sort of opposite ideas that we're going to be distinguishing when we're talking about an ordered list of vectors in R2. Clockwise and counterclockwise. Okay. How are we doing? Everybody on board? Now, of course, let me throw out there, of course, sometimes it's neither. Right, and so, the vectors might be parallel, or one of the vectors might be the 0 vector. There's all sorts of little anomalous little cases there. I'm going to point out that in all such cases, the pair is linearly dependent. And so that's the way I'm going to describe sort of the third option. And this is I suppose every so often that happens. But most of the time, if you have an ordered list of vectors, clockwise or counterclockwise. Okay. All right. Now, this is a natural idea. It was arguably a lot more natural back in the 70s, which I have to admit I do remember. And there was hardly such a thing as a digital clock. All clocks were like that one, right? And now your clock is, your wristwatch is only digital if you kind of put it in that mode, right? It used to be there was only that one mode. Anyway, nevertheless, still a very natural, relatable geometric concept. So let me point out some properties of it. I like to say they're mirror images of each other. And what I mean by this is if you have a pair, let's look at A and B here. This A and B, as drawn here, that's a counterclockwise pair. Right? If you take a mirror image, if you reflect over a line, well, the resulting pair, A prime, B prime, clockwise. Right? So this is what I mean when I say clockwise and counterclockwise are mirror images of each other. So pretty believable. I'll also notice that if you trade the positions of the two vectors, so if you replace, you put the A where the B was, put the B where the A was, like so, this is what we call trading the positions of the vectors, then that changes the ordering. In other words, what had been counterclockwise turns into clockwise. And you can see it right here, that what had been counterclockwise turns into clockwise. So now that's just another property of this idea of handedness, and I think it's a pretty easy buy. The last one I'll notice here is that it's independent of rotations. Namely, if you take a pair of vectors, excuse me, again I keep saying that, if you take an ordered list of vectors, and if each one of the vectors you rotate by a given fixed amount, let's say we rotate all these vectors by, whatever, some fixed amount. Well, then the resulting list is going to have the same handedness, the same ordering. If this is counterclockwise, then when you rotate them both, still counterclockwise, right? And this would be sort of the equivalent of if you look at a clock and notice which way the second hand's going. If you turn your head like this, the second hand's still going the same direction, right? So not a surprising fact. Okay. So why am I talking about clockwise and counterclockwise, making sort of what I'm going to call obvious geometric statements about clockwise and counterclockwise? Is because it's the perfect segue, sort of relatable analogy to a more sophisticated idea I'm going to talk about now, and that is what would be the three-dimensional version of this. What if you're in 3 dimensions? You're looking at 3 vectors, again, not just a set of 3 vectors, but what if you have an ordered list of 3 vectors in R3? Can you talk about a clockwise list or a counterclockwise list? Nah, not really. That'd be a pretty weird clock. Right? So, what's kind of like that? What's the equivalent sort of thing? And the best answer I'm aware of is not clockwise, counterclockwise, but what we're going to call right-handed and left-handed. And I'm going to gesture my way through this to communicate what we're talking about here. So let's start with what I mean by a right-handed list. Now, do keep in mind the order matters. Okay, A is first, B is second, C is third. So A first, B second, C third. And I say that this is what we're going to call a right-handed list. And here's why we call it right-handed. So there's a little gesture you're going to do with your right hand, and it's arbitrary choice, right? But arbitrary things are good for communicating, setting standards, and communicating consistently with other groups of people. So here's the idea. The gesture you do, index finger, right hand, by the way, index finger in the parallel to your palm. Middle finger bent in the way that middle fingers want to bend. Please don't do this move. Right? So, index finger parallel to the palm. Middle fingers bending the way they want to. And with this kind of arrangement, now you can kind of move your hand around however. Do what you've got to do now to get those 2 fingers, index finger being first, middle finger being second, pointed in the same directions as A and B. More to the point, pointed in the same directions as the first vector and the second vector. Well, your thumb then points on the same side of the plane defined by A and B, as this vector C here. You'll notice. So this is what we call a right-hand list. Because the C vector, when you use your right hand, when you follow those rules, the third vector is on the same side of the plane as your thumb. Now, by contrast, let's look at this other collection, or this other arrangement here. And again, A is first. B is second. C is third. And now let's play the game and see if this can I make this, is this a right-handed list? You can read, of course, and see that it's not going to work. But let's follow the rules. Okay, so first, second. Now, I've got to arrange my hand in some way or another to get my first index finger pointed in the direction of A. And now I got to figure out what I'm going to do to get my middle finger. And again, no, I'm not allowed to do that. I'm going to try to, what do I have to do to my middle finger to get it to point in the same direction as B? And I point out I have to turn my hand like this. And I can do it, there's no problem. So index finger in the direction of the first vector A, middle finger in the direction of the second vector B. Fine. But now notice my thumb is pointing on what you might call the bottom side of the plane defined by A and B, which is not the same side that C is. So this is not a right-handed list. ABC, if these are the vectors ABC, is not right-handed. But I claim it is left-handed because first vector, second vector, third vector, no problem. So in the same way that, it's weirder, sure, right? But in the same way that clockwise and counterclockwise are kind of geometric descriptions of the order in 2 dimensions and are opposites of each other, same for right-handed, left-handed, just in 3 dimensions with 3 vectors. Okay, and again, there's the sort of the other cases where something bad happens. And if you think through all the possible cases where neither right nor left works, what you're going to notice is that all of those are cases where the 3 vectors are linearly dependent. Again, so that's our third possibility. Yeah?
So we went to R4. Will there also be 3 options, or will there be more than 3 options?
We have to have a much more abstract conversation if we're going to talk about how to do this in R4. And hands don't work because our hands are 3-dimensional. And so in the same ways we had to abandon clock faces when we came up to 3 dimensions, we're going to have to abandon hands in 4 dimensions. And there's not really a good sort of geometric way to think about it. It's you have to get more abstract. And we're absolutely not going to do that in this course. Yeah. Yes?
What are ordered list of vectors for?
Oh, you'll see in a minute. Yeah. Well, first, I think I'm gonna say you're gonna see in a minute. So it's not that we're going to solve problems with this particularly. It's that this is going to unavoidably come up as just kind of a truth of certain kinds of math that we're going to see. And there's going to be information on the page, and the question's going to come up. What does that information mean? And the answer of what that math means, it means this. And why you care about it is I don't know. There are certain facts of physics that relate to it, but that's not really what we're going to focus on. Yeah.
Do the vectors have to be perpendicular?
Nope, not at all. So that middle finger, when you do this, you bend the middle finger, you might only have to bend it a little. You might have to bend it a lot, but they don't have to be perpendicular. And likewise, the third vector doesn't have to be exactly in the perpendicular direction of the thumb. It just has to be on the same side of that plane that the thumb is. Yeah. Okay, so here's why I say this is very much the 3-dimensional version of clockwise, counterclockwise. It's because they are mirror images of each other. If you trade the position of 2 vectors, that changes the order, and it's independent of rotations. It's got the exact same 3 properties that clockwise, counterclockwise had. Mirror images, trading changes the order, independent of rotations. So the analogy is extremely strong. Now let's take just a little bit slower take through this. I claim they're mirror images of each other. I think it's a pretty easy pitch. Right hands, left hands, mirror images of each other. I think that's relatable. This one you just have to kind of gesture your way through, but if you have a list that's right-hand order, such as this one that I've drawn here, if you change the positions, if you trade A and B, for example, right? So it was A first, B second. Now it's B first, A second. So I swapped just those two vectors. I claim that changes the order. And so, again, pretty easy gesture process, thought process. So let's see if I can do this. So ABC and BAC. Right, same three vectors, but if I order them differently, right hand turns into left hand. Okay. And again, independent of rotations. And this one, I think the easiest way to see this is just for me to do that. Look, if you rotate the vectors, then if I can do it with my right hand, then when I rotate all the vectors the same way, I can still do it with my right hand because I can rotate my right hand. Okay. All right. So, yeah. So this is I'm going to say this is a geometrically natural idea. And where it comes up will reveal itself in a few here. Okay, now I will point out, by the way, one last, that there is no sort of two-dimensional version of this property. There's a neat fact about right-hand order and left-hand order. If you cycle the list, cycling means that I'm going to take the third one and make it second. I'm going to take the second one and make it first, and I'm going to take the first one and bring it all the way back around and make it third. That's what I'm going to call cycling. And if you cycle a list of three vectors, that preserves the order. So ABC is a right. Let's see if I can do this. ABC is a right-hand order. And now let's see. I claim that BCA is a right-hand order. There you go. So ABC, BCA. Yeah. Try not to make any rude gestures to anyone while you're doing this. Yes.
Could you also cycle it the other way to get like CAB?
Yep. You can cycle as many times as you want in whichever order. Yep. Totally. Alrighty. Yeah. Okay. Now we're gonna stop talking about order for just a moment. We're going to talk about determinant now. And again, determinant's a property. It's an object of linear algebra. And it's very interesting, and there's a million things you can do with it in linear algebra, as I know you know. I want to talk about some geometric features of determinant. So we're going to start with a scenario where I have an ordered list of vectors in R2. Switch back to highlighter. And from this ordered list, we're going to do a couple of things. First thing we're going to do is we're going to take that list and we're going to generate a matrix by whatever the first vector is. We're going to make that the first column, and whatever the second vector is, I'm going to make that the second column. So if you have a list, you can make a matrix. Okay. If you have a matrix, of course, that defines a linear transformation, right? T of x is equal to ax. From the linear transformation, I'm going to now define a parallelogram by saying, I'm going to start with the unit square arbitrarily. And if I have a unit square, and if I have a linear transformation defined by a matrix, defined by a list, well, I can talk about the image. I can talk about what are all of the outputs. Let's see, I'm running out of colors here. I guess I'll use dark blue. Okay, so we've got that parallelogram there. Real quick, I will observe, and it's kind of a neat, think about it. Think about what we know about linear algebra. When you have a linear transformation, remember the columns of the matrix are the images of the standard basis. Well, the columns of the matrix are A and B. And they are the images of the standard basis vectors, and so therefore, the image of E1 is, in fact, A. It's that first vector A. And the image of E2, I am really out of colors at this point. I'll use the image of E2 is B. Okay, so I haven't really said anything yet. I've made some stuff, but I haven't made any real assertions yet. But I've got a list, I've got a matrix, I've got a linear transformation, I've got a parallelogram. Okay. With all that said, let me start actually saying stuff now. I claim that the area of this parallelogram, that area is equal to the absolute value of the determinant of the matrix. So you take this matrix here, take its determinant, take its absolute value, it computes an area for you. And it's a really surprising result. You think about it, in a naive scenario, the way we compute this area is, well, we probably drop a perpendicular, and I'd multiply, height times length. Well, how am I going to drop that perpendicular? Well, I'm probably going to think about this angle and that magnitude and sine and cosine or something, and that would compute this distance. And, of course, that's a square root because it's a magnitude. And I have some annoying calculations. Here I'm computing it with, again, three-function arithmetic, which is super surprising that would work. Everybody with me? Okay, yes?
What exactly what is S? What do you think of S as?
S is the unit square. So let me label that with so this is that's 1 and that's 1. Yeah. The reason I need it to be the unit square is because I need these to be the standard basis vectors. And because we know cool things about the images of standard basis vectors. Yeah. Okay, so determinant. What do we know about determinant then? What does this say about determinant? Determinant computes areas, which is shocking. Okay. There's more. Notice this, the thing that computes area, it's the absolute value of the determinant. So I took the plus or the minus, what we call the sign of the determinant, I just threw it out the window. Ignored it completely because it's only the absolute value that tells me the area. So, well, what about that sign that I just threw out the window? What does the sign indicate, if anything? And it turns out the sign indicates something really important. The sign tells me the order. So, again, this, it's not that I set out to understand order and found that determinant is the answer to the question. It's that we were thinking about determinant for other reasons. Determinant has a plus or a minus, and well, the answer is, and by the way, I'm not going to prove this theorem, and you're not responsible for the proof of this theorem. But the punchline is, the sign of the determinant tells you whether that list, and by the way, don't forget, the order matters, and we are talking, notice A is listed first, right? So that direction is first, and B is listed second, and so that direction is second. The sign of the determinant tells me whether this ordering, this first, that second, is clockwise or counterclockwise. And specifically, now you can see the way I have these vectors drawn in the picture here. This is clearly a counterclockwise order, and counterclockwise. Oh, see here. Counterclockwise corresponds to the determinant being positive. So just by looking at the picture here, I should have done that in green. Sorry. Just by looking at the picture here, the fact that this is clearly counterclockwise tells me this matrix, I don't even know what the matrix is, but I can see from the picture the determinant has to be positive because the list is counterclockwise. So, neat fact. And the other way, of course, as well, of course, there's, you could have vectors such that your first vector, let's suppose that that's A. And let's suppose that this is B. Right? If that's A and B like that, well, then AB is clockwise, and clockwise means the determinant's negative. Again, not going to prove this fact, I'm just asserting it, but that's the result. Okay. Yes?
What's this plane inverted?
Yeah, right. So that's the next thing I was going to get to. So what I've done here, I've made statements about this pair of vectors and whether the pair of vectors is clockwise or counterclockwise. Here's the thing, though. Don't forget that pair of vectors. That vector is the image of E1, and this vector is the image of E2. And I know that E1, E2 is always counterclockwise because, well, they don't move. They just sit there. E1 is here. E2 is there. That's counterclockwise. So let's think now about what the linear transformation does. The linear transformation here does a lot of things, and maybe you can see it's like it's taking space and kind of maybe rotating it a little bit. Then there's kind of a shearing maybe in that direction. Maybe there's a magnification. But nothing got flipped upside down. Because this list that I started with is counterclockwise again. It just is. And as I've drawn it here, their image list also counterclockwise. So in this case, there was no flipping. Nothing got flipped upside down. Whereas, on the other hand, let's suppose, again, it went the other way. And suppose that, let me get rid of these labels because they're just confusing me. Where is my, okay, here we go, orange. Let's suppose that was the first vector, image of E1. And let's suppose that was the second vector, image of E1. Well, then that list is now clockwise, and what does the linear transformation T have to do to turn a counterclockwise list into a clockwise list? Well, you can stretch or magnify or shear all you want, and counterclockwise is going to stay counterclockwise right up to the point where you flip it over. And so when the determinant is negative, there has to have been a flip over. And that's what I'm calling an inversion. Here I'm saying the plane is inverted. Because then, flipping it, if you think about it, flipping over you can think of as being kind of like reflecting through a line or, something like that. Okay. All right, great question. So you segued perfectly for me there. Okay. All right, well, there's a three-dimensional version of this. And it's all the more shocking. Oh, yeah, I'm sorry, question.
I'm sorry, what does that plane squish?
Oh, yeah. Well, that's right. I guess I should say some things about that. Think about what would happen if these two vectors were dependent instead of what I have drawn here. If the first vector were like this, and if the second vector, if it were like that, well, then my parallelogram, instead of having a parallelogram like this that has some area to it, well, the parallelogram would be kind of like that, right? And so all of the area inside of here, the image of all of this area would be not another piece of area. The image would be nothing. And so in some form or another, what the linear transformation does is kind of squish things down to flat. Yeah. So that's what happens if the determinant is 0. Yeah. Okay. All right, so there's a three-dimensional version of this, and what's beautiful about it is if you didn't know this theorem were true, and if someone were to just say, hey, here's a two-dimensional theorem, take a wild guess what the three-dimensional equivalent is going to be. The obvious guess is exactly true. So if you have a list, you can form a matrix. First vector, first column. Second vector, second column, etc. Just like on the previous theorem. If you have a matrix, you have a linear transformation. You can take a unit cube. Keep in mind the unit cube is where the edge vectors are E1, E2, and E3. If you look at the unit cube and look at its image, then you get it's not a parallelogram. It's kind of a three-dimensional version of that. It's called a parallelepiped. And being as it's three-dimensional, not two-dimensional, you'd probably guess that the absolute value determinant gives you the volume, and you're right. And you'd probably guess that the leftover, the plus or the minus, the sign of that determinant, well, it can't tell us clockwise, counterclockwise, because that's not a thing in 3 dimensions. But maybe you would think it tells us kind of the three-dimensional analog, namely right hand or left hand. And you'd be right. Correct, I should say. Not right, correct. So it's really exactly the same thing as the two-dimensional version. And so not shocking that it's true, but shocking that the analogy holds. What? Very weird. And by the way, let's take a moment to recognize how extremely handy this is, because how would you compute this volume without this awesome fact here? You'd be dropping a perpendicular from one vertex down to the opposing plane, and you'd have so many angles to think about, and it'd be a trig nightmare. Or it'd be unthinkable almost. Otherwise, snap, 3-function arithmetic, nothing to it. Okay. Oh, again, last case, if the list is dependent. Well, dependent would mean that these vectors over here kind of all in the same plane, and that means that your parallelepiped would be, I'm not even going to try to draw that, but it'd be flat, and that means that all of this volume would be squeezed down into a flat, no volume. And so everything's squished. So, squished. Okay. All right, so highly analogous, very interesting facts about determinants. Okay, now on to, question.
So the determinant would still be 0 if it squished into R1.
Yeah, that's right. There's different kinds of squishing. So you can take volume and you can squish it like this. That's what you might call sort of squishing it down into 2 dimensions, right? But you also could squish like you could strangle it, like you could, squeeze it down into like a line, right? We wouldn't say R1 because R1 refers to a collection of points that have only one coordinate. This is a line in space, right? But I know what you're getting at. But you could squeeze it down into 1 dimension. Or you could even just compress it down into a point. In other words, you could have the zero matrix. Yeah, and quick observation I'll make, and this is just a flashback to linear algebra. Which of those it is would be determined by the rank of this matrix. Y'all remember rank from, All right. Okie dokie. So on to cross products, finally. The namesake of the section, and we're just now getting around to mentioning it 35 minutes into the talk. So cross products, in order to really talk about cross products, it turns out we're going to need to talk about determinants, and we're going to need to talk about this geometric facts that we just got to talking about, and we're going to need to talk about right-hand order, left-hand order. And so that's why we've been doing all this other stuff, is because it's going to show up with cross products. I'm going to start by just writing down a formula Here's the formula for cross product. Kind of a weird formula, granted. Here's an alternative way to think of the formula. You can think of cross product instead as what I like to call a symbolic determinant. It's I hesitate to call this a real determinant because when you take a determinant, you're supposed to take determinants of matrices. A matrix is supposed to have elements that are supposed to be real numbers. And look at this weird move I've done. I've got vectors now sitting in the spots where there should be numbers. So that's creepy. Not really clear that, are we allowed to do that? It's just unsettling, right? So let's not worry about whether that's legal or whether that's a matrix. I just want to use this as what I'm going to call a symbolic sort of bookkeeping tool. If you were to ignore possible crimes related to what I've done here, just kind of don't worry about that, sweep that under the rug. Computationally, it would give you exactly the right thing. Now, for whatever it's worth, in my life, I have only ever memorized that formula for cross product. I have never memorized this formula. I don't trust myself. Right? It'd be too easy to mess it up. Right? I know at some point I'd be like, oh gosh, is it A1B2 or is it A2B1 minus A1B2? Which way does it go? And I'd get it backwards. Right? But this over here is really easy to remember. Standard basis vectors across the top. Let it slide. Right? First vector in the next row. Second vector in the last row. Take a determinant. I've long since memorized the formula for determinant. So I might as well capitalize, take advantage of that fact. So much easier to remember. Okay, and now here's where I'm going to start not proving things. If you were to compute a dot product with a cross product, and now you see that's what I have written here, dot product with a cross product. What you'll notice is that it's equal to a determinant. And in particular, here let me make a different color choice here. A dot product with a cross product is a determinant. Keeping in mind, first vector, first row, second vector, second row, third vector, third row. And it's just such a compact and it's just so clean how this gets written down. It's lovely that it's just so, everything worked out. What are the odds? Right? Highly suggestive that this is an important formula, and it is. Good thing to make sure you know. By the way, why is this true? Well, it's algebra, and I've got the algebra here, and you can read it if you'd like. But this cross product that's just copied from up here, and just multiply it out. And if you multiply that all out, and if you take this determinant, well, sure enough, it's exactly that. That's just a plug and chug confirmation. Okay. All right, so this thing is called a triple product for, I think, pretty clear reasons. And this is what I like to call the triple product formula, because this is the neat way to interpret triple products is that they are determinants. So triple product are equal to determinants, yeah.
It wouldn't matter which side the seed is on, right?
I'm sorry, what?
It wouldn't matter which side the seed is on?
Correct, but if that's right. Dot product is commutative. That's right. I always write it on the left because I think aesthetically it looks better. And also you want to be careful moving things around unless you want to just be constantly checking yourself. Wait a minute, did I move? Is this one of the reorderings where you get a minus sign, or one of the ones where you don't? If you want to be constantly thinking about that, then yeah, sure, absolutely. What you say is absolutely true. But I like to keep my life as simple as possible, and always put the dot product on the left of the cross product. But that's personal superstition. Okay, so why do we care about this formula? The reason we care about it is because we understand dot product already quite well. We understand determinant pretty well. we've just introduced this thing called the cross product that we don't understand. And what we have here is a connection then between the thing that I want to understand and things that I already understand. So this is the foot in the door that's going to answer a tremendous number of questions for us. Okay, now again, here's where I'm going to start skipping proofs. Just facts, though, that you need to know about cross products. The cross product is always orthogonal to both of the input vectors. It's orthogonal to the vector on the left, and it's orthogonal to the vector on the right. Neat fact, cross products are always orthogonal to both of the inputs. Another way to say that, if you find yourself needing a vector that is perpendicular, or orthogonal to both of a pair of vectors, I got a couple of vectors here, I need something that's orthogonal to both of them. Use the cross product. It already is known to have that property. Alright, so again, there's a couple different ways to prove this. I'm sad that I don't get to tell you these, because these are cool arguments. But you can just punch it up directly with, see if the dot products are 0, that means they're orthogonal, you're done. But it's algebra and it's unintuitive. Take a look, if you are so inclined, to this sort of more geometric observation, which I think is really slick. I wish I could spend time talking about it. Okay, next facts. Triple products are kind of what you might call cyclic or something. You can do that same move where you take the vectors and you kind of move everything over to the left, and of course the other one has to go around to the other side. You cycle the order, and triple products are always the same. Now again, you can punch this up, with pure D algebra. Just take a deep breath and plow through it. It's extremely inelegant and unhelpful, really. Right? You don't learn anything from just plowing through that algebra. But there's also a clever way to see it that involves thinking about interpreting triple products as determinants, thinking about how you interpret determinants in relations to parallelepipeds, and observing that, same parallelepipeds. So I encourage y'all to think that through. But anyway, here's the fact. And then next one, this one is a harder proof. I want to make it perfectly clear. When I was in your shoes, learning this material for the first time, I never would have thought of this. This is super clever. The start of this argument, which I hope you'll take a look at, is to consider something which is neither of the objects that we're making an assertion about. Right? So the assertion is that the magnitude of the cross product is the area of the parallelogram defined by that pair of vectors. That's the assertion. And the start of the proof is for no apparent reason to think about this third expression that doesn't immediately seem to equal either. In fact, is not equal to either of the above the things that we're interested in. So very clever proof. Again, I never would have thought of this on my own. Somebody showed me this argument, and that it's lucky that they did, because otherwise, again, I never would have figured it out. It's way too clever. So anyway, again, not going to go through the argument, but it's very cool. This is a fantastic little exercise in thinking about the properties that we've talked about. Make sure that you know, though, that the magnitude of the cross product is the area of the corresponding parallelogram. Yeah, you had a hand. Was that a hand?
Yeah, I was going to ask what the right side of the equation was.
Oh, yeah. Thank you. This is a little notation that I may have invented. I don't know. But this is the parallelogram defined by the vectors A and B. So, those two vectors pointing like that, and then you make a parallelogram out of them. Does that make sense? Okay. And then, by the way, analogously, here I have, if you have three vectors, and if you have three vectors, it would be a parallelepiped, because there's three of them. Okay. All right, so neat fact. Related neat fact. If the cross product is 0, your list is dependent, and vice versa. So this goes both ways. Again, really cool fact. Again, really cool argument. Again, we don't have time for the argument, and you're not responsible for it, but it's something I need you to know as a fact. Okay. And then lastly, and here's one all of these facts you may have seen in Math 218, you may not have, I'm not sure. But this list is, let me say it wrong first, because it's, this is the way you're going to think about it most of the time. So I apologize in advance. I'm going to say this wrong. This list is always in right-hand order. If you look at A and then B and then look at the cross product third, this is sometimes called the right-hand rule. Any two vectors, when you cross them, the thumb will point in the direction of the cross product. It's not the other way, it's that way. So, right-hand rule. As I said it, again, a little bit wrong, because let's face it, it's possible that maybe one of these vectors is the 0 vector. Or maybe that's the 0 vector. Or maybe multiple are the 0 vector and there is no right-hand order. Okay, so it's possible that this list is dependent. There is that third possibility. So I can't say it's always right-hand order. What I can say is it's never left-hand order. That much is clear. Okay, but again, people call it the right-hand rule. No one calls this the not left-hand rule, right? That's just not convenient. Okay, so now, interesting fact, and by the way, this is an alternative way to present cross products in the first place. I presented the cross product to y'all as a formula. I wrote down the formula, and then from that formula you can make certain connections to determinant, and then use determinant to, all the arguments that I kind of glossed over here. So you can start off with cross product as an algebraic thing, and then prove geometric facts about it. Specifically, you can prove from the algebraic formula that it's always orthogonal to the inputs, that its magnitude is equal to the area of the parallelogram, and that this is always right-handed. You know what I mean? So you can prove these facts that we just did. Or you can do it in exactly the opposite order. You can start with a definition, and our book does. You can make this the definition of the cross product. And then you can I wouldn't say you're reasoning backwards exactly, but you can make a different collection of arguments and derive the formula from this geometric description. So again, our book does it. I think it's harder. I think it's more work doing it that way. So I like my way better. But take a look at the book's arguments. See if you like it. I think you're going to notice there's a lot of algebra in the book's presentation, and a lot more pictures in mine. Yes.
Is the area of the parallelogram A, B the same as the term, like some sort of term?
Tempting, right? Because you see the area there, right? But the problem is if you take the vectors A and B, you got to keep in mind these are vectors in 3 dimensions, right? Cross product only makes sense in 3 dimensions as we're defining it here. And so if you have 3-dimensional vectors but only 2 of them, then your matrix isn't square, and there actually is no such thing as determinant. Yeah, so it's just, you get a different answer because it's a different question. Yeah, different context. Yeah, great question though. Okay. Oh, and let me interject, that also reminded me, there are some homework exercises about a sort of a version of cross product that is in higher than 3 dimensions. And it's a weird thing because normally you think of a product as being what we call a binary operation. Give me 2 things and then we do something to them and out comes a result, right? So addition is binary because 2 numbers go in, 1 number comes out. Right? So the cross product that they define for higher dimensions is not binary. If you have 7 vectors in 8 dimensions, then you can talk about the cross product of that list of 7 vectors. So it's weird, but it turns out that this generalized cross product has a lot of analogous properties, and so some of the homework exercises are to kind of think through how how you can use those to do certain cool things. Okay, so you'll see that on the homework. Okay, so last product. If you switch the order of the vectors, then you get a minus sign on the cross product. And then the book doesn't mention these following ones explicitly, but I think these are worth noting. So first of all, the cross product is linear. And I made this observation, what was that, first day of class or soon after? I don't remember. I think it was first day of class. But if you use cross product with a fixed chosen vector to define a function, right? So my function t here is cross product with a. Right? So whatever vector x you give me, the way I compute the result is, what I do to x is cross product with a. That function is linear. And so if you write that out explicitly, I mean, here it is. There's the function. And you can see what this says is, if you do the linear transformation before you do the function, if you do the linear if you do the linear combination after you do the function, same thing. So you can see this is literally a statement of linearity, the statement of linearity of this function. But this is what it looks like algebraically. And you might be more inclined to say that this is like a kind of a distributivity of cross product, like a distributivity and associativity of cross product. So anyway, I like to just say that cross product's linear. And by the way, on either side, if you do it on the other side, still true, still linear. Very importantly, though, the cross product is not vector associative. It's scalar associative. We talked about that a second ago. But it's not vector associative. If you take these vectors, if you try to do like a sort of a triple product with all cross products, right? You're going to make up your own new kind of triple product. This is not a well-behaved thing. And you can't just move the parentheses around with cross products like this. So this is a very important thing to be aware of, heads up. Right up there with, matrix multiplications, not commutative. You can't switch the order of matrices when you're multiplying. Okay. The applications, again, this is in there for your curiosity. We're not going to focus on, I'm not going to test you on your knowledge of torque. But in case you're curious, where does cross product show up in the physical world? I mean, it's torque, for one thing. Right? The vector that describes how hard you're turning in an angular sense is a cross product. And then likewise, forces related to magnetic fields. If you want to know what is the force that results when a charged particle moves through a magnetic field, that force is a cross product. So it's it manifests in the physical world. Of course, it's also a really, really handy tool in math by itself. Okay, and that's we got to stop there. Sorry, I went a little over. We're done with 1.4. See y'all on Monday. Y'all have a great weekend. And don't forget my announcement I sent out right before class. I do have to end office hours 10 minutes early today. Apologies. Got a meeting I have to get to. So anyway, hope to see some of y'all at office hours.